advertise to you that the point of category theory, or like the method that we employ in category theory, is to study objects, mathematical or computer scientific objects, by asking what relationships they have with the other objects in the category. So today we're going to see a concept that's defined that way for the first time. So the thing that we're going to talk about first is that of terminal objects. So let me just give the definition. So an object, let's say T, in the category curly C is called terminal. If for every other object, well by other I really mean every object, but we also want to include T itself. Take out the word other, but we can kind of think of it naively as other. So for every object D in C, there is exactly one morphism from D to T. And often in this, when we have a terminal object, we denote this unique morphism by a streak. Okay, so as we see, we are specifying an object. We will show in a few minutes in this lecture that the terminal, if a category has a terminal object, it definitely doesn't always, then it's unique in some sense. So I will talk about the terminal object. So we're specifying an object in a category, the terminal object, in terms of its relation to all the other objects. And again, I say other in a kind of naive way, but then in this definition, we also need to check when Z is T. So when Z is anything in the category. Okay, so let's think about what this means. So here's an example. What's the terminal object in the category of sets? Yes, very close. That will come up later. Something also is real. Yes.
The thing that maps to an empty set?
Sorry?
Sorry, no, never mind.
I'm looking for a set. Yes.
Singleton sets?
Exactly, the singleton set. So yesterday I denoted it like this, so I'll keep denoting the singleton set like this, and it got also. So this is supposed to be like a little t, a small cap t. Might also denote the singleton with a star like that, as it's usually done in set theory. Okay, so let's check that this is the terminal object. So if we have any set here, we can indeed find a map. So first we need at least a map to the singleton. We can do lambda z dot t. We send everything in z to t, little t, and one guy in here. Okay. And if you have any other map, any other function from a set z to this singleton, which only contains t, well, it has to send everything to t. There's nothing else in there. Okay, so it will be of this form. Yes?
And if there's many arrows from T to itself, it won't be terminal.
Exactly. Yeah, so in particular, this statement, when we instantiate it for T itself, we find that there has to be exactly one morphism from T to T. And what morphism is that? The identity, exactly. And we know there has to be an identity from T to T, and so that can be the only one if T is terminal. Yes?
You said that terminal objects are unique, but it seems like there are infinitely many singleton sets.
Yes, good point. I gotta explain what I mean by unique. Any other questions? Okay, so here we have set. What about in type? exactly, the unit type. So I think that's probably what Anja called it last week. That's what Wendy calls it. So if we have the category type, as Anja described it last time, we have unit, which really, I mean, behaves basically like this guy. I think maybe also Anja called the one constructor in here, the one term in here, little t, something like that. So it's really, in type theory, the thing that behaves like this guy. The type with just one term, optical t. Okay, and so a terminal for exactly the same reason. We can form a map like this from any type z to unit, and any map to unit has to everything to t, so it'll be equal to that one. Okay, here are some maybe weird examples to stretch your understanding. What about in this category? So by this category, I made a category with one object. Maybe I'll give it a name, A. So we have one object A, and I haven't drawn any morphisms because there are no non-trivial morphisms. So of course there has to be the identity morphism on A, but I won't draw that because this is a course about category theory, so there's always that. What is the terminal object in this category? Yes.
It's A.
Exactly, it's A. So terminal object is A, and that's because we look at this definition for every object in C, and there's only one here, A. We look at this, possible maps like this, and we need there to be exactly one map like that. And of course, there is only one map in this category at all, it's the identity. So we have exactly one map from A to A, it's the identity. Okay, what about some other weird ones? Like what if I have a category, let me go a little circle on this. So what if I have a category that has just two objects, A and B, and again, the two identity morphisms that I don't draw, but no non-identity morphisms.
There's
What's
no
a terminal object?
none.
Yeah. Exactly, there's no terminal object, because if one of these were a terminal object, then there would have to be, I mean, exactly one, but at least one morphism from every other object. See that guy? Right, and when, let's say that one word we can use to think about categories, at least in these examples, is connected. So we say that a category is connected when you can get from one object to another by going via the morphisms, some of which you might be going like the wrong way through it. So there's some kind of zigzag of morphisms. And if you have a terminal object, like here, let me draw another picture. So if you have a terminal object in your category, you have a bunch of other objects here, then they all have arrows to the terminal object. So all arrows like this. Okay? And then we say that this category is connected because we can get from this object to this object by going to the terminal object and then going back. Okay, so we forget about the direction and we ask if it's connected in a graph theoretic sense. Okay, so the category with the terminal object is always connected. This guy is definitely not connected. So it doesn't have a terminal object. Okay, what about, let me just document this drawing. What about this category? Yes.
B is the terminal object.
Yeah, exactly. B is a terminal object. So we have to check that this collection of arrows and this collection of arrows has exactly one arrow. And we call this F. So here we do have exactly one F in the picture. And here we have exactly one identity. Oops, identity on me. Okay, good job. So, right, now in order to get further with my story about terminal objects, I need to talk about isomorphism. Isomorphism is an important concept in category theory. And to give a little bit of foreshadowing, when I say, like what I said a few minutes ago, that the terminal object is unique, it's unique up to isomorphism. And that's the notion of sameness that we care about in category theory. Yes?
So if we drew another arrow from A to B, B would not be, there would be no terminal objects anymore, right?
So if we drew another arrow from, like this way?
No, from A to B.
From A to B. Yeah, exactly. If we had another arrow from A to B, like G, then when we look at possible arrows like this, there would be two.
Okay.
And we need there to be exactly one in the So this category is connected, but it doesn't have a terminal object. So the implication only goes one way. If it has a terminal object, it is connected, but if it's connected, it might not necessarily have a terminal object. Okay. Right, so now I want to talk about isomorphism, because isomorphism is the notion of sameness that we care about in category theory. So, let's see. Definition. Two objects. In the category C, I should give them names, of course. Let's say X and Y, two objects, X and Y, in the category C are isomorphic if there is, or there are, I should say, I'm going to give it a definition slightly differently in my notes. If there are maps this. Okay, so now I've done something I haven't done before. So when I write this and this, I mean that F goes from X to Y, and then G goes from Y to X. Okay. So we need two maps like this, such that if I do if I do S and then G, I get the identity on X, which of course both go from X to X. And if I do the loop from Y to Y, so I do G and then F, this is the identity on Y. Okay, so I want to say something. Maybe first actually I'll fix that one. So we want to write, in this case, that X is isomorphic to Y. I mean, I'll read it out loud, but there's this isomorphism symbol. And you say that F is an isomorphism. We also might write like F from X to Y like this, or also like if I first write this on the board and then somehow we prove that F is an isomorphism, then just write a little squiggle to denote that as an isomorphism. And we often write F inverse or G. And similarly, if we start with G for some reason, we could write G inverse for F. So one thing I want to say here is that when we do category theory, I guess we're studying the object. Maybe some people in some situations would disagree with that, but we're studying the object kind of V as a morphism. So the notion of sameness that we care about with objects is isomorphism. We do not care about equality in category theory. Some of you might have heard that when you talk about equality between objects in category theory, that's called evil. There's a lot of work about what's evil and what's not evil. There are certain problems that arise when you're evil, so we don't want to be evil. We want to only consider objects up to isomorphism. But we care about arrows up to equality. Because here, for instance, I've written some equalities between two arrows, and also in the definition of category, I've written equalities between arrows. So we care about literal equality between arrows. But then we get kind of an inherited notion of sameness between the objects. That is not about equality between objects, but about morphisms between objects that themselves are the same up to equality. So we kind of use the equality of arrows and kind of push it down in some sense and get a notion of sameness between objects. Yes?
So, from the graph theory perspective, or from looking at the categories graph, are two objects going to be isomorphic if there is like one incoming arrow and one outgoing arrow, or is it something more complicated?
Yeah, so the graph theory perspective is a good first step. We definitely need these two arrows going back and forth between X and Y. But we need more information than what a graph carries we need information about the composition. The composition is not a piece of data that is included in the graph, but here we need to check that GF composes the identity and that FD composes the identity, and yeah, that's only something that we can calculate. Yeah, good question. Other questions? Okay, so, oh yeah.
You said the terminal objects are unique of isomorphism. Is there like a fast demonstration of that?
Sorry, I can't quite hear you.
Oh, you said the terminal objects are unique of isomorphism. Is there like a fast example of that?
It's not an example, I guess I'm gonna prove it in a second. Yeah. I mean, maybe you can think as an example, you can think about this terminal object, right? As someone pointed out, I made a choice by naming the inhabitant of the singleton, right? So there's like, I'm kind of like as big of a kernel as you can think of, many singletons. You can see the different symbol there, some of the different symbols. Many different symbols as you possibly can. So it's not unique, certainly not unique up to equality. Because if I have a singleton where I put true there and a singleton where I put false there, I mean, those are literally different sets. But they are isomorphic, and well, then it also requires you to know what isomorphism is in sets, which we'll say in a second. But first I want to ask a more elementary question, which is, let's go back to this example, I'll change this slightly. If I have a category with, let's call this F, one isomorphism F, so there's an implicit F inverse I didn't draw, but I wrote this, that's squiggly line, it has an inverse. If I have a category with two objects and an inverse, it's somehow like the three inverse categories. What is the terminal object here?
It's A and B because they are isomorphic. So it's A, B.
Yeah, exactly. So it could be A or B, they're isomorphic, so they are the terminal object. And it is the case that if you have a category where all the arrows are isomorphisms, so we won't talk about that so much in this course, but it's called groupoid, so it is important for some kind of category theory, then everything in a groupoid is a terminal object. Okay, suppose A and B are the terminal object, and we need to check, so let's just say we want to prove that B is the terminal object. The situation is completely symmetric. So to prove that B is a terminal object, we have to check that these two things have at most one arrow. There's most one arrow like this, and at most one arrow like this. Okay, so here we have F. So I want to say that this is the only arrow from A to B. But really, there are more, or you might think that there are more, because you can do F, and then F inverse, and then F, and then F inverse, and then F again or something, right? You can do that as many times as you want. But the F and the F inverse cancel each other out. Right, so as many times as you go around the loop, you're just going to get F as a composition. And similarly, we have our one map identity from B to B. You might think like you could do F inverse and then F, but by definition it has to be the identity anyway. And if you did it like 4 times or 2 loops, then you would still get the identity on B. Okay. So let's think about when isomorphisms are in set. I'm going to bring this down. So I mean, you might, if you take a class where you use sets, you might have used this word actually, but what's an isomorphism in the category of sets?
Bijections?
Yeah, exactly, bijection. So yeah, people often just use the word isomorphism for bijection sometimes, but like the set specific word is bijection. So taking a class about like logic or set theory, you often prove that if you have 2 functions, f and g, that are inverse to each other between 2 sets, so in the category of sets, that's the same as, let's say, f being a bijection in the sense that it's both a surjection and an injection. Okay. Right, so these are bijections or often just isomorphisms. And you can ask also in pi, the pi is really very much like set, so it's just also some kind of, well, isomorphism. Maybe a more interesting example is our category crush. from yesterday. So what's an isomorphism in prop? Yes. Sorry. Yes, double implication, which I would call bi-implication. So we need an arrow, so we have two propositions, P and Q. We need an arrow from P to Q, we need an arrow from P to P. And we need their compositions to be equal to the identity. But we talked about last time, that prop is thin. It has at most one arrow between any two things. So just like last time, if we want to check these two equalities for our two implications between P and Q, then we're looking at arrows for implications from P to P and implications from P to Q. But there's only one, or there's at most one. So these two things, they live in a collection or a set of at most one element, so they have to be equal. So we don't actually have to check that very precisely. So the thin category, like prop, we just need two arrows going back and forth. So these are bi implications. Okay. So, let me give an exercise now. So a good exercise, let me recall right here. A good elementary exercise now is if F is an isomorphism, then F inverse is unique. Because I think there was some fact proven on the slack of learning part of this. Okay. If you want, you can try to prove this without looking at that. So what I mean is that if F satisfies this definition with some G, but it also satisfies this definition with some other guy H, I want you to prove that G and H are the same. There's also a similar fact if you've taken like group theory or something, it's the same fact. Okay, so here's another useful fact. Right here. So this kind of justifies why we use isomorphism as our notion of sameness in category. So if F, give this a name. So if we have an isomorphism between two objects, X and Y, let's call it F. Then for any object Z in our category, we have the following fact. So we have that homomorphisms from Z to X are in bijection with homomorphisms from Z to Y. So now maybe we can think, like I said yesterday, that it's kind of wishy-washy about what I meant by a collection. Maybe it's a set, maybe it's a type. Maybe we can just bring out that these are just sets. So if X and Y are isomorphic, then the set of arrows from Z to X and the set of arrows from Z to Y are in bijection, are also isomorphic. Okay.
So if you have X and Y, they're isomorphic if there's at least one bijection. If there's, you can still have many bijections, right?
Yes, definitely. Yeah, so just think about the category of set. You could have like the Boolean, so a set with two elements, and it has a bijection with itself as just the identity, but it also has a bijection with itself that it did not, so it takes true to false and false to true. Or think about the natural numbers, there are many bijections from the natural numbers to themselves. Yeah, so we have an isomorphism like this, and it's given by F. So, on the identity of it, maybe I'll name it now, so it's usually called something like F lower star. And I will define it in the proof that I'm about to give. So we have this, and we also have another fact that you might expect. So we also have the fact that morphisms out of X are the same as morphisms out of Y.
And F star is not a morphism in the category, right? It's like an arrow between arrows, so it's in a higher thing, or is that
Yeah, so let's say that these are sets. They can also be types if you want. You need to pick up some kind of foundation. So let's say that these are sets. Then these things are objects in the category of sets. So, I could just forget that forms a category and just say, okay, we know what bijections are from earlier in our lives or something, but really this is not isomorphism in the category of sets. Okay, so this justifies, I want to say that this justifies the concept of isomorphism in an arbitrary category, because if you worked with sets in your life, you know that once you get past like the class about the relevant Randall criteria, if you start using them, you know that you don't care about sets up to equality, you care about sets up to bijection. Like how exactly you represent the natural numbers doesn't actually matter when you start using them. So we only care about sets up to bijection. And we kind of use that fact that that's how people work with sets, bootstrap it to say that that's how we should also work with categories. Because if we want to study the objects in a category just by looking at the amount of morphisms that come in and out, we cannot distinguish between two isomorphic objects because they have basically the same morphisms going in and out. Okay, let's prove this. Maybe I'll just prove a little bit, maybe just some exercise, kind of check that what I'm saying is correct. So really I just wanted to define the bijection that goes back and forth. And maybe I'll only do it for the first bijection because the second one basically the same kind of principle. So define this map, F star. So F star is going to go from left to right, of course. So I'm going to take an arbitrary guy in this Hom set of x. So it's something that looks like this, like G from Z to x. So I'm going to take this. 2, then x, f, or G, x, something like that. And by this I mean really the composition. Maybe I could write a little thing here. So I mean composition. Okay. So we take an arrow from Z to x, and now the verb is post-compose. We post-compose it with f. We just continue along with f, and then we get a morphism from Z to y. And I said this is a bijection, so there should be a guy going backwards. So then I can find the inverse by sending, now I want an arbitrary guy, let's call it h, from z to y. I can't really switch these. Okay. Let's look at this. So we send an arbitrary morphism from z to y to basically the same thing. So first we do h, and then we do f inverse. So then we do the exercises to check that these two things, these two maps, f lower star and f lower star inverse, are actually inverses of each other. But maybe I can just do it out loud real quick. So if we do G, and then stick an F on the end of it, then we go this way and stick an F inverse on the end of that, then the F and the F inverse will cancel out. Right? So when we compose them together, they're the identity. So then we're just left with G. When we go this way, we put on an F, and then an F inverse. And they cancel out, so we're left with G. If we start with H, then we put on an F inverse, and then if we want to go this way, we put on an F. So it's going to be H, followed by F inverse, followed by F, then the F inverse and the F they cancel out. So therefore, an isomorphism. Okay, and let me tell you that it's not something I'm going to get this week, but this implication that if we have an isomorphism of objects, then we also have these two isomorphisms of objects. It's actually a different only if, and it's something that's called the Yoneda lemma, or it's one way to think about what the Yoneda lemma says. And actually, you only need one of these. So like this isomorphism implies these two, but you only need one of these to imply that guy, and then it will also imply this one. And if you have heard anything about category theory, you might have heard of the Yoneda lemma, and the Yoneda lemma is used to like prove almost everything. So the if and the only if in this one are very important for calculations. Yes.
So, the intuition here is that if you have two isomorphic objects, then any arrows from those objects to other things are also isomorphic to arrows from another object, even if those arrows are subjective.
I don't know what surjective
Or,
means.
sorry, if I have these two objects and they're both homomorphic to each other, and I have some arrows, including some arrows that aren't reversible, that are going off in different places, even the arrows that are not reversible will be homomorphic with the arrows that are not reversible that are coming out of this guy.
Do you mean isomorphic?
Isomorphic, yeah, I don't know.
Yeah. So maybe you can have a picture in your head, like that you have in some categories. You have X and Y that are isomorphic to each other, and then you have like the rest of the category. Right, so you have some object here, and you have like maps like this. And yeah, the possible maps to X are the same as the possible maps to Y, in the sense that once you compose this as isomorphism, you get all the possible maps to Y and vice versa. That's true for every object in the category. Yeah, so when we think about the category, like all the other objects in the category, as kind of probing these two objects, then you can't tell the difference between them. Okay, so now I want to show that terminal objects are unique up to isomorphism. So that's what I want to do. So let's do that. Let's see. Okay, so here's the dilemma. Terminal objects are unique up to isomorphism. Actually, I'm going to prove something stronger, which is true, that terminal objects are unique up to unique isomorphism. So I answered a second ago someone's question about whether there could be multiple isomorphisms between two objects, and for terminal objects, there can only be one isomorphism between them. Up to unique. Okay, so here's the proof. So we want to consider two terminal objects, of course, and then we're going to show that they're, well, first of all, isomorphic, and second of all, that there's only one possible isomorphism. Actually, the second part will be obvious after the first part. So we're going to consider two terminal objects.